Perspective projection matrix. In this video, we discuss OpenGL perspective projection, which is defined by the command gl frustum with parameters L, R, B, T, and F. L means left, R, right, B, bottom, T, top, and near, F, far. These parameters define a frustum as shown in this diagram. We have the XYZ axis, and this is the origin, and we are looking along the negative Z axis, and this is the near plane, and this is the far plane. Now, in the OpenGL transformation, projection transformation, this frustum will be transformed into a 2 by 2 by 2 cube with say this point L, B, negative n mapped to this point negative 1, negative 1, negative 1. And this point at the far plane mapped to 1, 1, 1. Okay, so this point is R, T, negative F. Okay. So in general, a point inside the frustum XYZ will be mapped to a point inside this cube with coordinates xc, yc, and zc. And all the scenes inside the frustum are projected onto the near plane. And scenes outside will be clipped away, but one can always use model view transformation to move objects into the frustum. Note that the Z-axis does not need to pass through the frustum. It could be outside. And the derivation of the projection formulas are still valid, even if the Z-axis is outside the frustum. In practice, the viewpoint or eye position may not be at the origin, but we can use model view transformation to move the eye position to the origin, and of course all the objects will be moved accordingly. And then the eye may be looking at a certain direction, and the object is not inside the frustum. We can use rotation to rotate the object into the frustum, so that it will be projected. We will discuss model view transformations in another video. Some acknowledgements. Many figures used in this presentation are copied from the internet. We sincerely thank the authors of the figures. Also, most information presented here is obtained from this book by Fore. Now, before we proceed, let's discuss homogeneous coordinates. So let's take a brief review on this topic that OpenGL uses, and we will use that also in our derivation. Homogeneous coordinates have 4 components, say x8, y8, z8, and w. To get the physical coordinates, we divide the components by the fourth one. So this becomes x8 over w, y8 over w, z8 over w. And then we discard the fourth component, that's 1. And that becomes our physical components, x, y, z. So x equals x8 over w, y equals yh over w, z equals 6w. Conversely, xh equals x times w, yh equals y times w, ch equals z times w. Okay. And now let's see how the projection on the xy plane at z equals minus n, that is the near plane, is done. Okay. Now this figure shows the procedure. Okay. This is the x-axis, okay, and this is the z-axis, and this is the origin O. So we assume our I is here and looking along the negative z direction. Okay. So the near plane is at z equals negative n, because this is the origin. So a vertex xyz will be projected onto the near plane at the point x dash, y dash, z dash, which is equal to negative n. Okay. And of course this is the line of sight, so this is a strict line. And given xyz, we want to calculate the projected coordinates x dash, y dash, z dash, which is minus n. And this can be done easily using similar triangles. So we know that we have two similar triangles here, and the ratio of x dash over x is equal to n over negative z. Okay. The z is negative, so negative z is positive. Okay. So it is given by this formula: x dash over x equals n over negative z, or x dash equals x times negative n over z. Similarly, we have y dash equals negative n times y over z. We know that x dash need to be within the range L and R, and y dash need to be within B and T, y dash. Okay. Now we discussed that the LB negative n will be mapped to a negative 1, negative 1, negative 1, okay, this point to this point, and LT negative F will be mapped to a 1, 1, 1. Okay. By using these conditions, okay, we can solve for x dash, y dash. Okay. So we want to transform, okay, this to canonical coordinates xc, yc, so that, okay, xc is within negative 1 and 1, yc is within negative 1 and 1. And this could be done using a linear transformation. So we can write xc as a times x dash plus b. Okay. We have similar equations for yc. Okay. We need to solve for the constants a and b. Okay. And this can be solved using the boundary conditions we just mentioned. Okay. So x equals negative 1 when x dash equals 1 L, and x equals 1 when x dash equals R. So substituting this into this equation, so we get negative 1 equals AL plus B, 1 equals AR plus B. So we have two equations, two unknown. We can just solve that. So we can subtract this one from this one. So 1 minus 1 we get 2, and A R minus L, B cancels B. So we get A equals 2 over R minus L, and substitute this back to this. We get B equals 1 minus 2R over R minus L. That's equal to minus R plus L over R minus L. with this, from 6 and 2, we substitute this A and B back into here, okay, and X dash, okay, into here. Remember, X dash is equal to minus n X over C. So we get, okay, X equals, say, AX dash plus B, which is given by this and this, okay, and then X dash, okay, is this minus nx over C. So we substitute that in, so we get this equation. Okay. As we mentioned before, in homogeneous coordinates, xh is equal to wh times xc. If we make wh to be negative c, then xh equals wh times xc equals negative cz times xc, and with this, okay, so we get this term, the negative c cancels, okay, so we have 2n r minus l times x, and then plus, okay, because this term times negative c becomes positive, okay, I have a z here. Okay. And now we can express this in an OpenGL matrix form, like the following. Okay. OpenGL matrix is 4 times 4, so these are the homogeneous coordinates, xh, yh, zh, wh, okay, is equal to this times xyc1. Okay, now so wh is equal to c times negative 1. Okay, and xh, okay, these two terms, okay, you have x times this, okay, plus this times c, so it is this term. Okay. And then of course 0 times y is 0, 0 times 1 is 0. Okay. The coordinate yh can be similarly obtained by doing the replacement L replaced by B, R replaced by L. So the projection matrix is like this. Okay, this is what we had. So this for the YH, okay, R replaced by T, L replaced by B, so we get this. Okay, and this term corresponds to this. So YH equals 2n over T minus B times Y, okay, plus T plus B over T minus B times C. Okay. And so what left is to find these two matrix terms, M22 and M23. Okay. And from matrix multiplication, we have CH, okay, equals M22 times C plus M23 times 1. Okay. So expressed in this equation. Okay. But we know that the canonical coordinate CC is equal to ZH over WH, and WH is equal to negative C. So by substituting this in, CC equals ZH over negative C, so the Z cancels, so we have negative M22 plus, okay, M23, okay, divided by negative C. Okay. And we know that CC is actually artificial. It is not related to the projected C value, which is negative n. Okay. And also Z equals negative n when CC equals negative 1, and Z equals negative f when CC equals 1. Substituting this into 15 here, then we get these two equations. Again, we can easily solve them. So we can subtract this by this. So we get these solutions. So M23 equals minus 2fn over f minus n, and then substitute it back, we get m22 okay, equals negative f plus n over f minus n. Okay. So the complete matrix of 13 okay, becomes this. Okay. So we put these terms here. Okay. Say, for example, we can test it using an example. If L equals 0, R equals 2, B equals 0, T equals 2, N equals 1, F equals 3, must substitute into this matrix. Okay. Then the projection matrix okay, can be calculated. So we get 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, negative 2, negative 3, okay, and 0, 0, negative 1, 0. Okay. Now this matrix can be generated by this OpenGL command, GL frustum 0 to the left, to the right, 0 bottom to T, okay, N is 1, F is 3, okay. And now let's check this with a program, okay, to make sure that this is right. We have written a simple program. Okay. So in this program, nothing special. We have a routine that print out a 4x4 matrix. Okay. And so we set the matrix mode to a GL projection, okay, and then load the transformation matrix to be identity, and then we execute GL frustum, okay, 0, 2, 0, 2, 1, 3, the same as this one. We expect to have a matrix like this. Okay. So we get this projection matrix, put that into the 4x4 array, and then we print out this matrix, okay, for the when we execute display for the first time, okay, and others are not relevant. Okay. Here we draw a Y sphere. We have to move that into the frustum using this transformation. Okay. So now let's compile this. So this is the make file, nothing special. And we execute this. And you can see that this is the projection matrix, okay, which is the same. Okay, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, negative 2, negative 3, 0, 0, negative 1, 0 is the same as this. Okay, that's what we expected. Now, let's see where the point 0, 2, negative 1 is projected to. Okay. We expect it to be mapped to the upper left corner of the canonical box. So that means xc, yc equals negative 1, 1. Okay. Let's check. Then we basically use this. Okay, to find xh, we use this row 1, 0, 1, 0. So we have 1 times 0, okay, plus 0 times 2, plus 1 times negative 1, okay, it is negative 1. And then for y h, we use the second row. Okay, so we have 0 times 0, and then 1 times 2, okay, and 1 times negative 1, okay, and then 0 times 1. So this is negative 1. Okay. That is what we expected. So that's correct. Okay. By the way, this is x8, y8. So we need to do one step more. But here the W component is equal to negative Z. Z is equal to negative 1, so negative, negative, we get 1. Okay? So that means XC equals YC is equal to the homogeneous coordinates divided by 1, so it is negative 1, 1. Okay? So that's what we expected. Okay? Now in OpenGL, the comment group perspective with parameters FOV, aspect, NF also creates a projection matrix. Okay? This is a special case of GL frustum. Okay? Now here, FOV is the field of view, the angle theta subtended by the near plane in the y direction from the point O, the origin. Aspect, or A, is the ratio of width W to H. This W is not the homogeneous coordinates. It represents width, okay? And height is H, okay, of the near plane. Okay? It assumes that the center of the near plane is at the point 0, 0, minus n. Okay? So the z-axis, okay, passes through the center of the near plane. And so from here to here is n, and this whole angle field of view is theta, so this is half of it, so theta over 2, this is theta over 2. Okay. And from here to here is 8, okay, the height is 8. Okay. So this is half of it, 8 over 2. Okay. So here we have A equals W over H. A is the aspect ratio. Tangent theta equals H over 2 over n. Okay, this length divided by this length. Okay, that's tangent theta over 2. Okay. Or H is equal to 2 times n times tangent theta over 2, and W is equal to H times A. Okay. So this is a special case of the previous projection in which the center of the near plane is at 0, 0, minus n. So we have T plus B equals 0, R plus L equals 0. Okay. Because the center is 0, 0. Okay. And T minus B is the height, H, okay, which is equal to 2 times n times tangent theta over 2. And minus R minus L is the width, okay, or H times A. Okay. And so the terms at 18 the terms here, okay, can be simplified because R plus L is 0, so this becomes 0. T plus B is 0, so it becomes 0. So we have these terms, 2n over R minus L. R minus L is the width, and T minus B is the height. Okay, so we substitute that in and simplify it. So it is the 2n cancels 2n, so we have 1 over tangent theta over 2 that is equal to cotangent theta over 2. Okay. And the other term is 1 over A cotangent theta over 2. So the matrix for this becomes 1 over A cotangent theta over 2 is 0, 0, 0, okay, and so on. Okay. Say for example, consider GL frustum negative 1, 1, negative 1, 1, 1, 3. Okay. So this can be replaced by a group perspective command with n equals 1, f equals 3, and aspect ratio equals 1. Okay. And tangent theta over 2 is equal to 1 over 1. The near is 1, okay, and the half height is also 1. Okay, so tangent theta over 2 equals 1. That means theta over 2 is 45 degrees, or theta is 90 degrees. So the command that represents GL frustum negative 1, 1, negative 1, 1, 1, 3 is good perspective 91 13. Okay, so this aspect ratio, this is the near, this is the far, and the corresponding matrix, you just substitute this in. Theta over 2 is 45 degree, cotangent is equal to 1. Okay, and so this term is 1 and this is 1. Okay, and these two terms are the same as before. So this is the projection matrix, okay, for this command. Okay, now we can check this again. So we change our projection matrix. Okay, we comment this out. Okay, now let's try this first term first. So we have negative 1 1 negative 1 1 1 3. Okay, and we compile this. Okay, and execute. Okay, so you can see that. Okay, that's what we have. Okay, all these are zeros. Okay, 1 1 negative 2 negative 3 negative 1. Okay, and now let's try the other one. We comment this out and use the full perspective. Okay, so light 1 1 3, that is equivalent to the first term of this. Okay, and we compile this and execute. Okay, so again you can see that we get the same result. Okay, 1 1 negative 2 negative 3. So you can try this yourself also. Now, this is the beauty of mathematics. Once you could derive the formulas of an operation, you understand that Fore and its constraints and conditions that it works. Okay. So you may want to go for the derivation yourself. Okay. Yeah. Thank you for watching. Okay, bye.